So we had started with the necessary and sufficient conditions, and we had seen the first order necessary equation on Wednesday. We'd seen the theorem. We did 3 examples, the one which we finished yesterday. Then we did the proof for that. Then we started the first order necessary with inequality constraints. So those were the KKT conditions which I said. Those were the 5 conditions, and we did the theorem, and we are going to do the example today. So this is done, and we're going to go from here. What we do today is we'll do the second order necessary sufficient with equality constraint, and then we'll do the second order necessary and sufficient with the inequality constraints as well, and bring a double circle to differentiate the two. So we'll finish all of these today. We'll do one problem also, so that you can do problems on all of them in the tutorial, and then Thursday we can start linear programming. So that's the goal. So you may think I'm taking too many lectures. This is the 6th lecture, and we'll take another tutorial on Monday, which means that we'll be covering almost half of what I had to do, because I take 12 lectures and approximately 6 tutorials, so that's 18. So the reason this will normalize is that then 31st and 1st is Diwali, so you don't have to be there for that Thursday. So we'll make it free, so you don't have to worry. So this extra lecture kind of compensates for that. Before I go ahead with this, there is a note I wanted to write which I didn't write yesterday for the first order necessary equation. The first order necessary conditions for a minima and equality constraints. So the theorem here had said if x star blah 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 is a local minimizer of the problem and is regular for the constraints, then we had written that ai of x star is equal to 0. This is a note in the first order necessary for the equality constraints, I going from 1 through r. And the second one we had written is gradient of fx star is a linear combination of the gradients of the constraints. Correct? And we had done those 3 examples on them, and then we moved to the inequality constraint. This can be also written in terms of something called as the Lagrangian of the optimization problem. I should have told you this earlier. This will show up in your papers which you're doing at a lot of places. By the way, feedback was good. I think most of it is fine. I'll just summarize and do some changes as you go along. I think one of them was the application. So the application has been covered in your lab. So what I'll do in the lab, I'll start picking a couple of papers and going over the content of the paper which matches with the class. Because otherwise I can't do it in class. It will take the whole lecture to cover one paper if I try to do that. Questions, problems, of course, that I'll upload. Pace wise, I think most of you find some say it's slow, some are saying it, most of you are saying it's fine. And I don't think there's nothing alarming there. Okay, so what do we define as something called as the Lagrangian function, which is written with an accent. This is written as f of x minus summation I going from 1 through r lambda I ai of x. So to carry the objective function and the constraints together, what was the problem which we are trying to solve? Minimize f of x with respect to x and subject to ai of x equal to 0, I going from 1 through r, f going from an n-dimensional space to a one-dimensional space. This is the original objective function, original optimization problem. So what the Lagrangian says is it combines the two together. It says you can, rather than write objective function separate and the constraints separate, you can put them together. That's what we did. It's a function of x and lambda. Lambda we are saying is lambda 1 through lambda r. That's the lambda vector. x1 to xn is the problem variable. So now the question is, how can you write these two in terms of the Lagrangian? And this is an equivalence which you can think about. So how would you get the first condition from the Lagrangian? Sorry. X star so we can put X star here, that doesn't matter. But how would I get the first condition and how would I get the second condition? That's what I'm asking. What should I do to the Lagrangian variable? If lambda star is 1 1 1, then what happens? Correct. Aviral. Okay. So what if I say write this? What will this be? I'm taking the gradient of the Lagrangian with respect to the lambda variable. Right? What is lambda? So if you do it, this term will be 0. Lambda variable, it means that you're doing with respect to lambda 1, lambda 2, lambda r and putting that in a column vector form, right? This is lambda 1 times a1, lambda 2 times a2, lambda r times ar. So if I take d over d lambda 1 of this thing, what will I get? What will I get? A1, right? The lambda 1 star will become 1, so you'll just get A1, lambda 2 will be 0 differentiated, lambda r differentiation will be 0. So this will be nothing but A1 x star. And similarly, if you do it with respect to lambda r, you will get AR of x star. So this condition, the first condition, is equivalent to saying the gradient of the Lagrangian with respect to lambda is equal to 0. Correct? Everybody with me? How can you get the second condition? With respect to x, correct? Because there is a x playing a role here and there is a x playing a role here, right? So if I write gradient of Lagrangian with respect to x, this will be gradient with respect to, do I have to write a x here? Do I have to write an x here, subscript for the gradient? Why? Yes, Sanjana, right? Because there's only x here. The only variable is x, so you don't have to be explicit about it. The Lagrangian is a function of two, x1 to xn, lambda 1 to lambda r, so we are specifically separating it. So if you combine the two, these two equations, you can say this is equivalent to saying that the gradient of the Lagrangian with respect to x lambda and x star both is equal to 0. Everybody okay? The reason I switched to Lagrangian is that these sufficient conditions are necessary in the second order requires you to work with the Hessian of the Lagrangian. So it's important to know it. Although you can work, you don't have to, for the first order, you don't have to explicitly write the Lagrangian. You can avoid it if you want. Everybody okay? So this was a note here. Now we are going to start this example for the first order necessary with the inequality constraints. I'm not going to write the 5 which is written in your notebook. We just did it yesterday. We'll directly do the problem. I think once now that you know the Lagrangian, all your papers will make more sense if you read them. No, most of them they form a Lagrangian function, and there is also many of your papers have a technique called Lagrange relaxation as well. which you can read in your papers, but I'll cover that in the lab so that you can see the real life application of why Lagrangian is so important. Okay, so we're doing this example here. So the example goes like this. So it says minimize f of x, which is x1 square plus x2 square minus 14x1 minus 6x2, and they're given two constraints subject to c1 of x is equal to 2 minus x1 minus x2 greater than equal to 0, and c2 of x is 3 minus x1 minus 2x2 greater than equal to 0. So now you have to solve it. So what will we do? How will we solve? Help me with this. What will we do? Solve it in the sense, apply the KKT conditions, apply the Karush-Kuntaker conditions to get the candidates for minimizer, because I have not told you the sufficiency conditions, so you can't find me a minimizer, but you can find me a candidate for minimizer. Okay, what was the first condition in the KKT? Equality. There is no equality constraint, so nothing to do. The second said these should be true, so let's write them explicitly because we're going to refer this. And 3 minus x1 minus 2x2 greater than equal to 0. What was the third condition? Gradient of the function is a linear combination of gradient of the constraint, both equality and inequality. We don't have equality, so we'll just write function of inequality constraint. So the gradient of the function is, help me write it, it's 2x1 minus 14, 2x2 minus 6. This is gradient f, and then we have got two inequality constraints. So we'll have mu1 times the gradient of the first inequality constraint, which will be minus 1, and plus mu2. The second one is minus 1 and minus 2. Everybody with me? We've written gradient of the function, linear combination of gradient of constraints. What was the C condition? Sorry, D condition was, so we wrote the feasibility condition, we wrote the Lagrange multiplier condition, the fourth condition, the D condition, was the complementarity condition, which says that the product of mu1 c1 is equal to 0, so mu1 2 minus x1 minus x2 equal to 0, mu2 times 3 minus x1 minus 2x2 equal to 0, and then the last was the non-negativity constraint, which says mu1 is greater than 0, mu2 is greater than equal to 0. So your half your work is done here, है ना? Now you have to solve it. So how do you solve it? One way is that the problem in solving a general inequality constraint, whether you do the first order or you do the second order, is these inequalities bother you quite a bit. I mean, had it been equal to 0, then you would have number of variables and unknowns, substitute and find it, right? So if you try to even do all this substitution, it will get really cumbersome. You can try it at home. I usually do it in class, but we have less time, so I'm skipping that part. You can convince yourself that when you do all the substitution, it will become hairy. So the easier way to do is to make cases. The cases go by defining whether the inequality constraint is active or inactive at a certain point. So we start with the case, let's say what case I have taken. Both constraints are inactive, let's say. Where are the both constraint inactive? The point where I'm trying to check it is a minimizer or not, the x star or mu star which I'm trying to find. Both constraints, const dot is constraints inactive. Now things will get easier for you once you have defined this case. How many cases will we have? 4, 2 to the power 2, because inactive, active, and you've got 2 constraints. And if I had 3 constraints, how many cases will I get? 8, 2 to the power 3, right? So those, because active, inactive for all of them. So if both are inactive, which would mean that C1 is strictly greater than 0, C2 is strictly greater than 0. This is what inactive means. Correct? I'm not writing x in, but it means it's a function of x. Now the very first thing to start off with is D and then go backwards. Check D, E, C, A, B. Check all of them in that order. Why we work with this guy? Because this brings the most simplification to your set of equations. So if C1 and C2 are greater than 0, you will get mu1 is 0, mu2 is equal to 0. So you checked the D condition already. The D condition is fine. Is the E condition correct? Is mu1? So that's also done. We'll go back to the C equation. So to do the C equation, you put both of them equal to 0. You will get x1 as 7 and x2 as 3. Correct? Let's go backward now. Substitute x1 7 and x2 into C1 and C2 in the B condition. So your C1 would be 2 minus 7 minus 3, which is minus 8. Correct? Which is less than 0. You don't have to check C2 even, which means that this case is not valid. It's not satisfying the constraint. Okay. Let's do the next one. Alright. So the next case is, I'll not do all and just do 2 cases. The rest we'll say only C1 is active and C2 is inactive. So the one which gives us the most simplification is, of course, anyways. So in this case, we're saying C2 is inactive, which would implies mu2 is 0, C1 is equal to 0, which implies mu1 could be anything, we don't know. But we would want the product, if even it is negative, it will not bother because the whole thing will be 0, so we don't know. So we're going to use this. So we started with this condition. We started with this condition and we were able to show that mu2 is 0. Now we have to check for all the others. So the very first thing I'm going to do is take this guy and I'm going to take C1 is equal to 0. So these 2 equations and this equation I'm going to pick. So I'm going to write that down. So this would be 2x1 minus 14 minus mu1 or plus mu1 equal to 0, because mu2 is 0. You get 2x2 minus 6 plus mu1 is equal to 0. And then you have got C1 is equal to 0 from this. So you have got 2 minus x1 minus x2 equal to 0. So you have 3 equations and 3 unknowns. So you solve for them. So what do we get? We get as x is equal to 3, 1 and you should say x star by the way, and mu1 is 8. Okay. So mu1 is 8, which means that now we satisfies this. We are done with this equation. We are already done with this equation because you use this. We are already done with this equation. So what we have not checked is this equation and the product of them, is greater than equal to 0 or not. So the very first thing I'm going to check is C2. So C2 is 3 minus x1 minus 2x2. So that will be 3 minus 3, 0. Something is wrong. It's minus 1, sorry. It's minus 1, so this will turn out to be 2, which is greater than equal to 0. So you're done with this. And now is the product of mu1 and we took C1 equal to 0, so this is anyway satisfied. because we already showed C1 is equal to 0, we enforced it. So irrespective of the mu, it doesn't matter, and all are positive. Mu1 is positive and mu2 is equal to 0. So if you want, you can write this as this and put the star also. So what this becomes, this is a candidate for minimizer. Do I have to check for regularity? What did the theorem say? You needed to have, it's regular for the constraints that are active at X star. Which are the constraints which are active? C1 is, it's only one constraint, so nothing to check for the regularity. It's independent, it's a single. If there were two, then I would have checked the regularity also. Alright, so that is the case 2. Why don't you guys do the case 3? Tell me that. So we switch the other one, case 3 we'll say. In that one, C1 was active, no? So in this one we'll say C1 is inactive and C2 is active. Tell me if you get a candidate for minimizer or not. You can do both of them actually, if you have understood. Do you want me to do this third case, or you can do it by self? Do it? What's this answer? Could anybody got X or mu?
5 minus 1, 0, 4.
X star is? 5 minus?
5 and 5.
No, I think I am getting 14 by 3 and minus 5 over 3. This is what I am getting for this, and the second one is this. You can double check. So are these candidates for minimizer? Check your answers again and tell me whether they are candidates for minimizer till the time I write the next thing. Is everybody getting that?
Yes, sir.
So is it a candidate for minimizer? Why not?
C1 is
C1. So I think then I may have done it wrong. You can do this one also. This one is not a candidate for minimizer because one of the mu becomes negative, and here the C1 is violated. use the time and do this also, because this theorem writing will take a minute. So you can use your time. So minimize. Are you done? Did you get it? Same answer? Alright, so now you can write if you're writing the theorem, but I'm just going to finish writing and then explain. Okay, so we are now talking about the second order necessary and sufficient conditions with equality constraints. Like I'm doing equality first order, inequality first order, now I'm doing second order necessary and sufficient for equality, then we'll write the second order necessary and sufficient with inequality. There is a whole analogy, so once you know this one, then you know rest of it. So this is same, which you have seen earlier. If x star is a constrained local minimizer of this optimization problem and is a regular point of the constraints, then constraints at x star, then it should be feasible, and there is the Lagrange multiplier condition that the gradient of the function is linear combination of gradient of constraint. If you recall the unconstrained case, which Neminath had thought, what was the second order necessary condition there? The Hessian of the function was positive semi-definite. I mean, you went to the sufficiency, it was Hessian as positive definite, right? So the same analogy kind of carries over, that you have to work with the Hessian, but instead of working the Hessian, so there we had the function f, here we have the Lagrangian. Why? Because the function f, there was nothing else to worry in the unconstrained case. Here there were constraints, we took the constraint, combined it with the objective function, we call it as a Lagrangian. So there you were looking at the Hessian of the function, here we are going to look at the Hessian of the Lagrangian. So instead of so a direct analogy would have been the Hessian of the function is positive semi-definite. Here the Hessian of the Lagrangian is positive semi-definite. That would have been the simplest analogy going from the unconstrained case to the constrained case. Does it make sense? But that it turns out when you try to prove it, that's much harder condition. You don't need the Hessian of the Lagrangian to be positive semi-definite over all of the space. You need it in a small area of the space, which is defined by this. So the Hessian of the Lagrangian only with respect to x. It's not even saying only with respect to lambda. So you're making the hypothesis to be much easier or weaker for you. With respect to x is positive semi-definite, not on all over the space, but only on the null space of the Jacobian of the constraints. So of course, the details why this is true goes in the proof, but the thing you should remember, it's making your life easier. it would have been much harder to prove that the Hessian of the Lagrangian with respect to x, with respect to lambda, is positive semi-definite over all of the space. Rather, we just look at the smaller space. So if this is some sort of an n-dimensional space, saying that your matrix is positive definite for every vector inside this. That is how you prove positive semi-definite. You multiply with x transpose on the left, x on the right, and say this is greater than equal to 0 for, then it is positive. So rather than checking for all of the space, I will only check for vectors inside some smaller space which is defined by the null space of the Jacobian of the constraints. And I am not even going to worry about the Hessian of the Lagrangian with respect to lambda. I'm going to only worry about with respect to x. So how you write this mathematically, you can also write this statement. This is easy to remember. This is something that you will have to remember for the course. I mean, I don't do a memory test, but this is a base foundation of all the remaining necessary and sufficient. So remember this. In words, it's much easier to remember than mathematically. Mathematically, you would write this as n n transpose x star Hessian Lagrangian x star lambda star n x star positive. This is a sign of positive semi-definite. It's not great. This is a greater than sign, and this is a sign which defines positive semi-definite, slightly curved. So this where columns of this n matrix, this is an n matrix, span null space of J star. So here this looks more difficult to remember. That's why I wrote the wordings, which is much easier to not span. They form the basis. Sorry. So what you do, you find the Hessian of the Lagrangian with respect to x. You find the null space of the Jacobian of constraints. Do we have to worry about active or inactive here? Yeah. Others? Besides Abhinav? Yes, Saket. It's equality. Everything is active. When we go to the inequality case, then we'll have to worry about to carry the active inequality constraint as well. So you just take all the constraint, put them in the row format. That's a Jacobian matrix. Find its null space, and the vectors which are spanning its null space, forming the basis of it, will be your n matrix, and then you multiply it. This will become another matrix, and this matrix should be positive semi-definite. That's what it's saying. We'll do a problem. This will become much easier. So this is a second order necessary condition. Right now, before I do the example, let me write the sufficiency condition, because it's just a carry forward thing, which you can also tell me how to write. So if I have to write the sufficiency condition, what will I write? If x star is a regular point of constraints and if constraints meaning these guys, it's a regular point, and if what all is true, then what will be the sufficiency condition? Recall your unconstrained case. It's just, it changes the direction. If it is a regular point and ai of x star is equal to 0, I going from 1 through r, and gradient of the function fx star is a linear combination of gradient of the constraints and Hessian of the Lagrangian with respect to x is positive definite over the null space of the Jacobian of constraints. Maybe I'll write it so that you don't see two notations. Null space of Jacobian of constraints then what happens? It's a strong local minimizer, right? That's the difference which we go with the sufficiency condition. Then X star is a strong local minimizer. Everybody with me? Everybody comfortable? This, if this is not comfortable, don't worry. The next problem we do will make this easier for you to understand. But the direction reversing and changing semi-positive semi to positive definite from a weak minimizer to a strong minimizer, both are local at this stage. If your objective function in constraint form a convex problem, it will become a global minimizer. All that can be inferred from this. Okay. So let's do the problem. I'll let the theorem stay so that you can not forget about it. Why are we studying all of this? So eventually your goal will not be to take a problem and solve by hand. You will not be able to do it because the general problem will be inequality, and if you see those inequality 5 KKT conditions, the number of cases grow exponentially in the number of constraints which you carry. So it becomes so difficult to have so many cases. So we'll have to have an algorithm around it. Unfortunately, there is no general algorithm for a general optimization problem. So that is why there is algorithms for different types of optimization problem, which you have seen with me. The linear program you'll see, the quadratic program you'll see. The most general algorithm which we have developed for a general constraint optimization problem is called a sequential quadratic algorithm, which means you take this general problem with the inequality constraint, you transform it into a sequence of quadratic programs. And then you know the algorithm for the quadratic program which will try to satisfy the necessary and sufficient condition, and that is solve it. So that is the rest of the class until we finish the semester. That is where we are going. Okay. So let's do an example. First this one. So we'll do the same example which you just did with me a little while ago on the example 2, where we applied the necessary condition yesterday. Example 2 was done day before yesterday, I think, but it's the same problem. So this, you had minimize f of x is equal to x1 star plus x2 star plus 1 over 4 x star. I don't know what's wrong with me. I'm trying to do it in a hurry. Probably don't want to keep you waiting. Your tutorial after this? Lab. Okay, then stay 5 minutes extra. You remember this now, at least it's written there. So we'll apply both necessary and sufficient. Okay, this is your objective function. What were the constraint in that example 2? a1 of x was minus x1 plus x3 minus 1 equal to 0. a2 of x was x1 square plus x2 square minus 2x1 equal to 0. Flip your notes, those who are writing. Those who are not writing, don't worry. What did we do there? In example 2, we applied the first order necessary condition. The first order necessary condition said a1 of x was equal to 0, which is this guy. a2 of x was equal to 0. This was the A condition. The B condition was that the gradient of the function was a linear combination of gradient of constraints. I'm going to write it down again one more time. So the gradient of the function is 2x1. That's it. 2x2. And it's x3 over 2. It's all plus. There's a minus. It's all plus. Okay. And the constraints was lambda 1. The gradient of the constraint is 1, 0, 1 plus lambda 2 times 2x1, 2x2, 2x1 minus 2, 2x2 and 0. Yes, everybody with me, we have done this before. 2x1 minus 2, correct. Okay. So now you had these 5 equations and 5 unknowns. x3 minus 1 is equal to 0, x1 square plus x2 square minus 2x1 equal to 0. So when we solved for this, what did we get? The two candidates for minimizer. Tell me. 0, 0, 1 and this was x star and lambda star was half and the other one was, what was the other one? 203 and 3 by 2 and 11 over 4. This we had done earlier, so I had to write it down because now we start from here. So now the question is, what do you have to do? You have to apply the C condition. The C condition. So we'll apply the C condition, which is part of the necessary and sufficient. Both, if it turns out to be positive semi-definite, then we'll say it's just still a candidate. And if it is satisfied, then we'll say it becomes a minimizer. So what was the C condition? Hessian of the Lagrangian with respect to x. So we'll have to write the Lagrangian down, right? So what is the Lagrangian function now? Tell me. x1 square plus x2 square plus 1 over 4 x3 square. You can avoid writing the Lagrangian also, plus lambda 1 times x1 plus x3 minus 1 plus lambda 2 times x1 square plus x2 square minus 2x1. So now the question was, what is the gradient of the Lagrangian? I am not writing stars everywhere. Why do I need to find the gradient? Am I going too fast? Huh? Yeah, to find the Hessian, right? Gradient takes, when the domain is n-dimensional and range is 1, the equivalence of a full derivative, and this is the gradient function, which takes the partial derivatives. Now, but this gradient itself takes n-dimensional and goes to again n-dimensional space, because it's taking partials with respect to all the x's. So its domain is this, domain is this, and now you take the second derivative of this would be the Jacobian of the gradient, which we call it as the Hessian. Yes, everybody with me? You would have learnt all this with the Eminat, I assume. I'm just reminding you. So what is the gradient of the Lagrangian? You don't have to do much. It is the gradient of the function minus the gradient of, sorry, should be minus, you're not correcting me. It's the objective function minus the linear combination of the correct constraints. So if you take the gradient of the objective function and subtract the gradient of the constraints, then that's the gradient of the Lagrangian, which you have already done. This is it. Gradient of the function is a linear combination of gradient of the, so I'm going to write this down. So this is 2x1 minus lambda 1 minus 2x1 lambda 2 plus 2 lambda 2. That's the first one. The second equation is 2x2 minus 2x2 lambda 2. The third equation is x3 over 2 minus lambda 1. Everybody with me? You can do it from this also, but since you had done the work in the first order necessary condition, I just took that and wrote it there. Everybody with me? So this is the characterization of a derivative in a function of many variables. Now it becomes, the range also is, it's a vector valued function. The domain is 5-dimensional and the range is Three-dimensional. You've got three elements, right? It's a vector-valued function, function of many variables with 5, x1, x2, x3, lambda 1, lambda 2, and the range is 3 with vector-valued function. So now if you have to find the second derivative of this, that would be referred to as the Hessian of the Lagrangian, which would be the Jacobian of the gradient. Hello Venkatesh, I'm in a class. I'll call you back. Huh? I'm in a class. People, really? I picked your call and saying I'm in a class, still talking. Okay. Alright. I'm being nice not to ignore your call. Anyways, so we have to find Jacobian of gradient of the Lagrangian, which we refer to as the Hessian of the Lagrangian, but we don't have to compute the Hessian of all of the Lagrangian. I mean Hessian with respect to both sets x1, x2, x3, lambda 1, lambda 2. We only have to do it with respect to x, because it says Hessian of the Lagrangian with respect to x. So I don't need the Jacobian with respect to lambda, so I only need it with respect to x, which means that I will take the first element and differentiate with respect to x1, x2, x3. If I was doing it general, then I will do x1, x2, x3, lambda 1, lambda 2. Make sense? Okay. But I don't need that, so I only will do with respect to x. So when I do with respect to x1, I will get 2 minus 2 lambda 2. With respect to x2, 0. With respect to x3, 0. And if you were doing with respect to lambda 1, lambda 2, it will become 3 cross 5 matrix. But you're doing only with respect to x, so it's 3 cross 3 matrix. Making sense? It's a square matrix. With respect to x2, you will get, with respect to x1, the second element is 0. When you do with respect to this is 2 minus 2 lambda 2, and then 0. x1 will be 0, 0 and a half. Is that correct? So now we did one part of it. We had to find the Hessian of the Lagrangian with respect to x, which is the Jacobian of the gradient, Jacobian with respect to x of the gradient of the Lagrangian. Yeah. No, gradient is with respect to both. Sorry. The gradient is with respect to x only. Gradient is also with respect to x. We have ignored the lambda. To get to the Hessian with respect to x, you have to just carry the x all along. Everybody okay? Any other doubt? Okay. So now what we do is, you've got these two candidates. We're going to check the Jacobian of constraints. Let's first substitute the values of this inside. So this is 0.1. This is 0.1. This is 0.2. These were your two candidates for minimizer, which you got from the first order necessary conditions. Now if I substitute this guy into this, what do I get? So I'll substitute this. Lambda 2 is minus 1. This becomes plus. Lambda 2 becomes 4 and half. Okay, good. 4, 4, half. Now tell me about this matrix. It is positive definite. Why? Eigenvalues, or you look at the leading principal minors. The leading principal minors 4, 4, 1 ही है ना, कुछ गलत तो नहीं कर दिया? Something is wrong. I I got 5 over 2, 5 over 2 and half. Did I write anything wrong? Minus 7.
It's probably because it was 0.2 instead maybe.
No, it was not minus 1. It was minus 1 over 4. You told me wrong. Or I wrote it wrong on the board that time. So it was minus 1 over 4. Once you substitute this, you will get 5 over 2. Doesn't change your thing, but at least we should get the computation right. So 5 over 2, 5 over 2 and 1. Half, sorry. It will be half now. So now the leading principal minor is the determinant of this matrix 5 over 2, the determinant of this square matrix 25 over 4, the determinant of the full matrix is 25 over 8. So the leading principal minors are 5 over 2, 25 over 4 and 25 over 8, and all are greater than 0, which implies this matrix is positive definite. So first important observation is we were worrying about whether this Hessian matrix is positive definite over the null space of Jacobian of constraint. We don't have to even do it because it is positive definite everywhere. So you don't even check anything, which means it is a candidate for minimizer, but it turns out to be positive definite, not just positive semi-definite. So it is a minimizer. It is a strong local minimizer. When you do further, if you want to do it at home, it proved that it's a convex problem too, and it will turn out to be a global minimizer. I mean, I'm not writing it down, but at this point, you know, this point is a strong local minimizer. Everybody with me? Yes or no? Let's do it for the second problem. I'll not take more than 5 minutes, so you can finish and leave. But let me finish it because by next Thursday, now that it looks like nobody has a problem with 2 lectures, so we'll switch to 2 lectures on Thursday. By that time, you will not remember a thing. So it's better that I finish it today. Okay. So now let's look at point 2. So at point 2, what does the Hessian of the Lagrangian turns out to be? Tell me. Write it down. So that's minus 7 over 2, minus 7 over 2 and a half. This will it will turn out to be. So is what is the leading principal minor? Even the first one is minus 7 over 2. So you can't say that this is positive semi-definite or definite over all of the space, which means now you have to do the extra work and find the null space of the Jacobian of the constraints. So the Jacobian of constraints, how did we define it? Gradient of a1 of x and gradient of a2 of x. Put it in a row format. This is how we defined. So what is the gradients? You have written the gradients down. It was minus 1, 0, 1, 2x1 minus 2, 2x2 and 0. Once I substitute the values, it will turn out to be minus 1, 0, 1. What was x1 and x2? 2 and 0. So 2, 4 minus 2 turns out to be 2, 0, 0. This is here the Jacobian of constraint matrix. Correct? Yes or no? Louder.
Yes.
So now what do we have to show? First we show that is it a regular point or not. Then we'll find its null space. Is it a regular? Why? If you make this one 0, this will become non-zero, which means that the number of non-zero rows in the upper echelon form will remain as 2, right? So they are linearly independent, which means that it's a regular point, right? So now let's say R2 is R2 plus twice of R1. So this matrix becomes minus 1, 0, 1. This becomes 0. This stays 0. and this becomes 2. So this is your upper echelon form. The number of non-zero rows are 2, rank is 2. Hence the 2 rows are linearly independent. So it's a regular point, that's done. But now we have to find the null space. What is a null space of a matrix? Find the vectors which come out of solving Ax equal to 0. That is called the null space. You've studied before? Yes or no? So now what we'll do, we'll take this matrix. We'll say x1, x2, x3 equal to 0. You could have done it with that also. It didn't change. Doesn't change anything. So we'll say this is minus x1 plus x3 equal to 0 and 2x3 equal to 0. This will implies x3 is equal to 0, which is equal to x1. So you got that x1 and x3 is 0 and x2 is free. So which means that the the solution to this matrix times x is equal to 0 is 0, 1, 0 times this x2, sorry. Or want to write it like this, this is x2 and I can pull this x2 out, it will be 0, 1, 0 and x2. Everybody with me? So which means that this vector is forming the basis of the null space. What is the basis? That every vector in that space can be written as a linear combination of that, and that vectors itself are linearly independent. It is a single vector, so it's linearly independent. Does it span the whole of the space, or any vector in the space can be written as a linear combination? Yes, because x2 could be anything, and every time it will be the null space. Correct? So now what do we have to do? We have to check the positive semi-definiteness or positive definiteness of this guy on this space, the basis vector. So my n, which I was writing earlier, if you see n, will be defined as 0, 1, 0. Okay. So now what we'll do, we will check whether our Hessian of the Lagrangian with respect to x is positive definite with respect to this or not, which means I'll check for n transpose Hessian xl at this point. N is what? Okay. So I'll put this as 0, 1, 0 minus 7 over 2 minus 7 over 2 a half, and put this as 0, 1, 0. What will turn out to be? It will be a scalar. The scalar value turns out to be minus 7 over 2, which is less than 0. So this is not positive semi-definite over this null space, which means that this guy is not a candidate for minimizer. Remember how the necessary condition helps? The negation helps. Because if x star is a minimizer, then aix equal to 0, gradient of the function is a linear combination of constraints, and Hessian of the Lagrangian is positive semi-definite over the null space of Jacobian of constraint. Now that if this is not true, then it is not a local minimizer. So this is a strong local minimizer, this is not a local minimizer. Forget about strong, it's not, period. Everybody okay? Comfortable? So we'll do a lot of problems on this on Monday. 10:30 we keep the tutorial. And I don't get upset that I'm taking extra lectures. Like I said, for the Diwali, Thursday, Friday, you are free if you're going home. I also want to be free. Friday anyways is a holiday. Thursday is whatever Choti Diwali or something, so we'll keep it off so you can go home. Thursday is holiday. Achha, so anyways, we were missing a lecture, so it's good that we are covering it. Don't go. One more thing. So, last thing, whose lab is it? Surya Prakash, computer vision. Parallel. That's okay. It takes time to go there anyway, so who would come to know that whether the class came late or it took you to stroll a little slowly. So you can say that you went slightly slowly today. But let me finish this. So the last thing I wanted to write, you don't have to write, I'll upload these notes, but just listen to it. है ना? So the last thing was second order necessary and sufficient with inequality constraints. I'll show this on the next Thursday, but I want to just tell you so that the whole section is in principle finished here. So what was the KKT first order necessary condition with inequality constraint? They were the 5 conditions. The feasibility conditions, AI is equal to 0, Cj is equal to 0, the Lagrange multiplier conditions, the gradient of the function is linear combination of equality constraint, inequality constraint, the complementarity conditions that mu's and the c's are product is 0, and the non-negativity that mu is greater than 0. Now if you take the analogy of the equality constraint, same there, the same F condition comes into play there. So the theorem, if you're doing the necessary condition, would go the same way. You'll have it A, B, C, D, E, but you'll have the F condition, which will be exactly the same as this with a small change. The condition would be same, Hessian of the Lagrangian with respect to X is positive semi-definite over the Jacobian of null space of constraints. And when you go to the sufficiency conditions, this will be exactly the same. The F condition will be that the Hessian of the Lagrangian with respect to X is positive definite over the null space of Jacobian of constraints. The only caveat or the change is that now the Jacobian of constraints will only carry the active constraints, which means it will carry all the equality constraints because they are always active, but there will be a set of active constraints in the inequality constraints. So your Jacobian matrix will be larger. So the Jacobian matrix which you will define will carry the gradients of all of the equality constraints A1 through AR, but it will carry some C1, C4, CS, you don't know which one. If C1, C4 and CS were active at that point, then it will carry this guy with it. That's the only difference which will happen. Everything else will remain the same. Is that okay? Thursday when we meet, I'll show you these theorems before I start linear programming. But I wanted, in case Monday I end up adding a problem on this, you should not feel that I didn't tell you. Is that okay? All good? Alright. So see you Monday 10:30 for the tutorial. Thursday 2 hours for starting linear programming. There will be break for Diwali. That's how we do it.